Okay, thanks, Joe, and thanks for inviting me. So I'm going to talk about two projects that are somewhat related and that have to do with the idea of having orthogonal features in a deep network. So the desire to keep the weights that connect two layers more or less to be orthogonal. So as is very well known has been well known for many, many years, backprop through many layers in a deep, very deep network or in a very deep recurrence can be hard because you're going to apply these matrix multipliers again and again, and then you backprop, you're going to do a lot of matrix multipliers backwards, which can lead to blowups or vanishing gradients and these sort of things, depending on the eigenvalues of your matrices that you're dealing with. And so there have been several ideas have been proposed for resolving this issue. And so one paper, for example, last year by Andrew Sachs and Surya Ganguly and others suggested that maybe we could do something like pre-training, or maybe we can view pre-training, layer by layer pre-training, which sort of people got excited about starting something like 2006, as a way to orthogonalize weights. And maybe that's the reason why they help. Even though these ideas got a little bit out of fashion lately, because backprop actually does seem to work on fairly deep layers, deep networks. But anyway, let's stick to that idea for a little bit. Let's train an autoencoder layer by layer, maybe, in order to orthogonalize the weights, and then use that as an initialization for our deep network. So what would the autoencoder do? Basically, an autoencoder is nothing other than some reconstruction function. So that you give it an x, a data point x, and you reconstruct it using some reconstruction function, which for a single layer, simple, straightforward, vanilla autoencoder is going to come down to something like this. You compute a bunch of hidden responses based on some hidden nonlinearity, and then you multiply that with the output decoder matrix, and that's going to be your reconstruction. If a lot of those hiddens are going to be zero, which actually in fact turns out to be the case very, very often for a lot of nonlinearities like ReLU and sigmoid and so on, then you're going to end up just defining the output of this autoencoder, the reconstruction, as a superposition of those weight vectors, of the decoder weights, weighted with some activation of all those hiddens that ended up being active, being non-zero, right? Interestingly, typically that's something like 10%. So it turns out very often these activities are very sparse after training the autoencoder. So to minimize this, you would minimize to optimize this, to learn this autoencoder, you would minimize reconstruction error or something like this. The squared distance between your data and the reconstruction. Now, going back to the idea of orthogonalizing weights, assume that these weights that are active together, like the weights in the W that happen to go on together because for this set of hidden units turn on to be non-zero together, if they were orthogonal, so imagine this would be an orthogonal basis defined by those WK. Well, then, in order to minimize squared error, projection error, into your lower dimensional space, which you get from your sparse hiddens, we already know what the right coefficients should be. This is very basic optimization theory. They should be the inner product between your input and the weight vector. W transpose X is the coefficient you should use in order to project orthogonally into some subspace. And so we're training with the objective to orthogonalize those weights. But in reality, typically you don't use W transpose X when you train your autoencoder, because if you use, say, a ReLU activation function, you're going to have something like W transpose X plus a bias, typically, which is going to shift the activation a little bit. And so rather than using the activation that you should be using if you are after orthogonality, you actually use that activation plus some constant. Now, one could hope, of course, that those biases end up all being zero or something like that, in which case everything would be fine. But it turns out this is not the case at all. So here's an example of some autoencoders, a contractive on the left, denoising autoencoder on the right, trained on some CFA patches. And so whenever you get these nice Gabor-ish kind of features, and you look at the biases of the hidden units, it turns out they are all, or almost always all negative, very, very negative. And that might not be surprising, and actually people have pointed this out several years ago and on several occasions. It's kind of a repercussion of the desire to have sparse activations because, because if you have a negative bias, imagine you have your ReLU activation, like looking like this. If you have a negative bias, you're just going to shift that activation a little bit to the right, and so it's going to set more responses to 0 than in the case where you had a 0 bias ReLU. And by doing so, you get more zeros in your vector of activations of hiddens over hiddens, and so you get a sparser code. And so the fact that typically something like 10% of hiddens are going to be active is obviously related to getting those negative biases. So this seems weird because we know that we want W transpose X as the coefficient to reconstruct from the point of view of orthogonality, but that's not what we're using. We're using W transpose X minus a constant, like -4 basically for all hiddens. So here's another piece of evidence that suggests that this is somewhat weird, and that no biases as the coefficients, like W transpose X as the coefficient rather than W transpose X minus constant, is a good thing. A couple of years ago, Adam Coates and others from Stanford published a paper where they studied some good old-fashioned deep learning methods like RBMs, autoencoders, and stuff on CIFAR 10. They cropped patches and did some pooling and stuff like that, some concatenation, and then fed that into a classifier. And what they showed is that of all methods that you could use, it was k-means that outperformed all the others, and that by a large margin was the best. But it turns out that they didn't just use k-means, and it turns out in the end that it's not actually the k-means that made this work. When they used the k-means, they noticed that it doesn't actually work, and so they replaced the activation by what they call a triangle activation function. And what that means is that you compute the activities of all your k-means units, responses, and then you set all those to 0, which are smaller than the average. Now, it turns out that the average, if you look at it empirically, is basically always around 0. And so what they really did is they compute the activation. So it's just in a product because the data is contrast normalized. And then they set responses to 0 that are negative, that are smaller than 0. And so they basically end up using nothing other than a ReLU without a bias, without the shift as an encoding. And they showed that this works incredibly well. So we recently did something similar. I'm getting a little bit ahead of myself, but on the right side you see a similar experiment where we trained a contractive autoencoder on a permutation invariant CIFAR problem. So you just show the whole image, you train an autoencoder on that image, CIFAR 10, that's 32 by 32 by 3 color channels. So you train your autoencoder, you use those features, put them into logistic regression, and depending on what activation function you use, you get different performance profiles. And it turns out if you just use a 0 bias ReLU, then you also outperform everything else in this case being a sigmoid and the actual ReLU with which the autoencoder was trained that includes the bias, right? So you just throw away the bias and suddenly the performance shoots up. This is a bit weird to explain from the perspective of orthogonalizing, the desire to orthogonalize to make deep learning work better, because this is, after all, just a single or 2 hidden layer network at the end of the day. Because you just train an autoencoder, use those hiddens as features, and then logistic regression, right? So we tried a little bit to understand what the real reason is that orthogonality helps, and I'm just going to give some little insights here. We don't really have a complete story that really explains all of it. So here's one little piece of evidence, which I'm just going to mention very briefly because I don't want to get too technical into those details. It turns out that for autoencoders you can compute energy functions just like you can for a restricted Boltzmann machine by integrating basically the vector field that the autoencoder defines. So at the end of the day, it turns out that an autoencoder, just like an RBM, defines a probability distribution which is the exponential of some scalar function. And for an autoencoder with negative biases, the function is this one here on top. And for an autoencoder without biases, it is this function here on the bottom, if you do the math. And so what's interesting to note on the bottom is that if your weights, so Wx in this case denotes the matrix containing the weight vectors corresponding to hiddens that are active for a data case X. So all of this is going to be a function of X always. So what's interesting to note on the bottom is that if your weight matrix is orthogonal, then you're going to end up just computing an inner X transpose X here, right, the norm of X. And then that's going to cancel with the norm of X that you get here, and basically f of X is going to be constant. So for all hiddens that are active together, it is at least possible by orthogonalizing those weights to have a constant density in the whole region in which those hidden units are active. And the same cannot really happen in this case of the ReLU that has a bias. So just to give you an illustration of that, what that means is it's this one here. So if you look at the probability density defined by the model on the hypersphere, which is fine if which is completely sufficient if we contrast normalize our data, then that turns out to be some complicated structure, almost like clustering, like a whole bunch of blobs or something, in the case of an activation function, which is the ReLU. And it turns out to be a homogeneous region, like a multidimensional manifold, if you want, in the case where you remove the biases. So there has been another piece of work a couple of years ago by Matthias Bethke, a paper that is really, really interesting and very nice, but has been completely ignored by the community, in which he claims basically that orthogonal transformations are steerable. They give rise to steerable features. And so what I talked about here, about this density being homogeneous, uniform in a region, is basically just another way of phrasing that statement that Matthias and others came up with a couple of years ago. So imagine you have an image, and in that image you have a little feature which is, say, a little bit of a Gabor structure. Now, if you phase shift this Gabor around, and you represented the subspace that spans these Gabor features using an orthogonal basis, then all that's going to happen in the hidden representation is that you're going to perform a rotation in that space. If you hadn't used an orthogonal representation for that subspace, you would trace out an ellipse or something like that. So in that sense, Matthias claimed they are steerable because the same thing that happens in the data space is just going to be reflected in the hidden space of that representation, if you have an orthogonal representation. So this motivated us to play around a little bit with activation functions which are linear and do not contain a bias. So if you do that naively and you just take a ReLU, remove the bias, and train your autoencoder, you will notice that this is not going to work at all because that autoencoder is immediately going to overfit the data. The reconstruction error will turn to 0, and you're done. Which is because essentially this model has too much capacity, and you want sparsity, especially if you have overcomplete many hiddens. You need sparsity to make sure that you don't overfit. So there's a good reason for those biases to shift to negative, because you need sparsity for anything to work at all. Incidentally, the same is true when training RBMs. So whenever you train an RBM that ended up working, in the sense that you get Gaborish features, and then you look at the biases, you will always also see that they are negative. So what we did instead, we do still want that activation to be on this line here, to be linear, right, rather than being shifted around. So what we do instead is just threshold that linear function and define that as our activation function. This is very similar to spike and slab RBMs, spike and slab sparse coding and these kind of things, where you have two variables, one of which decides whether you're going to be active, and the other decides what the code is that you want to use. So this perspective suggests the utility of doing something like that being mainly that you get away with linear activations that way and get something like sparsity nevertheless. This function incidentally has also been called hard thresholding, and there are variations of it which we also played around with, like this one. It has also been called coring and various other things in the past, but it hasn't been, to the best of our knowledge, yet been used just as an activation function to train a model like an autoencoder. So if you do that, notice also that the fact that we slap activation smaller than threshold to 0 just means that the regularization is sort of built in. And because of that, we just train this model on some data without doing anything other than minimizing reconstruction error. So we don't add regularization or something like that. So this is like a 4-line of code implementation in Python when you use Theano or something. So here are some features that you get when you train this kind of model on 80 million tiny images, for example, or actually a subset of that. And you get this Gabor-like structure that you would hope to get. And notice this is just minimizing reconstruction error. There's nothing else going on. There's no regularization or anything. What was really satisfying to see was that on top of those Gaborish features, we also get faces like this one, or there's another one here, which a lot of you probably remember from the New York Times article where they talked about Google getting those using 8-layer autoencoders and stuff like that, trained unsupervised. So this is just a single-layer autoencoder with a funny activation function that also gives you these. I looked around to find cats desperately, but I didn't find any. But this was trained on 80 million tiny images, not on YouTube videos, so I think that explains that. So you can then take those features and apply them. So we also trained on smaller data sets like just CIFAR, which is a subset of the 80 million tiny images, and just did some experiments to see how well it works and so on. And it turns out it works pretty well. You get performance that is that pretty much goes to the state of the art. If you just train those features, plug it into logistic regression, and then look at the performance. It turns out that taking a contractive autoencoder rather than this, which uses vanilla ReLU units with bias, actually unfortunately outperforms this zero bias autoencoder by a little bit if you replace the activation function by a zero bias activation once you do the classification, so once you train your logistic regression on top. It doesn't outperform it otherwise. Actually, it sucks otherwise. It gives really, really bad performance if you don't do this zero bias trick. But then if you just plug the activation into an MLP, so if you just take your feature extractor, which is the autoencoder, followed by logistic regression, and you fine-tune the whole thing as an MLP, you get to something like 64%. And this is back with the ZAE, actually, which works a little bit better then. Which currently is, as far as I know, the state-of-the-art on the permutation invariant task. The state of the art having been 63 point something before. Okay, I'm just going to skip over this rest. So what's unfortunate, as I said, is that a vanilla autoencoder treated with a zero bias activation actually works a little bit better. But I think one reason to explain that is actually going back to Matthias Beke's steerable idea, which is to say that if your model, your vanilla autoencoder, is sort of doing something like clustering, then it ought to work very well when you have data which is somewhat low dimensional. That is, its intrinsic dimensionality is so low, or it's so concentrated in small regions in the data space that tiling that space with tiny little cells like this would actually still work. And so if that is the case, then that would suggest that as you increase the intrinsic dimensionality of the data, a vanilla autoencoder should work worse and worse and worse, whereas a zero bias activation function should work better and better and better by comparison to the other one. And this is actually what we were able to show. So here's a variation of that experiment where, rather than doing permutation invariant CIFAR, we do permutation invariant CIFAR patches. So we just crop the center patch just to have a handle on the dimensionality of the data. And so we take the center patch and make that our data. That's all. We just crop across the whole CIFAR data. But then we vary the size of that center patch and call that our data. And so as you if you fix the number of hiddens and increase the patch size, you see that the performance initially starts to get better. And then at some point you hit a limit of what you can do with those 500 hiddens, and then it starts to degrade. But the most important take-home message is that the TREG activation, so the zero bias ReLU activation, degrades much more gracefully than activation function that has a bias in there. With 1,000 hiddens, it looks similar, even though everything gets a little bit better, of course. And if you compare this model here, this autoencoder, it actually gets better and better and better, and it's best in this setup in the end, which is also not surprising because you cover much more of subspace if you have an activation function which can be active on one side of the data space and the other side of that subspace. So that sort of confirms the idea that there's something to this steerability and this uniform manifold region that we were hoping to get after with this. Recently, Johan Lin did some work, he's a grad student in Montreal, did some work on trying to use this in order to get deeper models to work better, going back to the initial intuition that orthogonalization might also help getting the weights to behave better when you backprop. So he wasn't able to get any reasonable results using ReLUs, not surprisingly, maybe. He came up with some other tricks like interleaving linear layers and stuff like that to reduce the number of parameters. Because if you have something like 4,000 hiddens and then another layer of 4,000 hiddens, you're going to get 4,000 squared parameters, which is a huge number of parameters. And so he was hoping to reduce that by kind of squeezing, putting in bottleneck layers, which helped a little bit, but it didn't really help overall to get towards the state of the art or something. But then if you tried ZAE, you just make the switch basically and do the pre-training with the ZAE. It just works beautifully and it kind of gives 10% better performance. And in the end, with this linear interleaving idea, he gets something like 65.8 or so, which is quite a bit above the state of the art on the permutation invariant task. Actually, just to mention, one of the reasons for doing this is that from a hardware perspective, convolution is actually quite a mess because there's nothing better than matrix multiplications, and that's the reason why deep learning started to take off the moment that people used GPUs, of course. Right? So GPUs are a really good match for matrix multipliers. And so why is that? Well, matrix multiply it's a computation that's as parallel as it can possibly get. You have a bunch of values, and then you have a bunch of completely independently computable units in the next layer, so when you do your matrix multiply. And so every one of these units can do its job completely independently from all the others. And at the same time, the stuff that this unit does is again just an accumulation of stuff, which is like a weighted sum, which again can be done completely independently from the other. And so a matrix multiply is beautiful from a hardware perspective because it's so parallelizable, it's so simple and so on. Convnets are somewhat like this as well. You can do matrix multiplies as well, but you always have to use something like im2col or some way to take your image and turn it into a stack of patches and then cache in on that beauty of matrix multiplication. And so part of the motivation of all this permutation invariant CFA stuff was to try to see how far we can actually get with something that simple, like matrix multiplies followed by nonlinearities. And so that's why we were sort of banging our heads pretty hardly against this. And so we were pretty happy to see something like 65.7. But then you can go further, and rather than training 4 layers, you can take 8 layers and still interleaving your linear layers and stuff, and always doing the ZAE pre-training. And then surprisingly, we get up to something like 70% almost. But Duhan didn't want to stop there, and then he thought, well, why care about permutation invariant if what we're really after is a fully connected net? So let's give up on permutation invariance, and let's just throw in extra data like deformations, rotations, affine transformations, and that kind of stuff. And then he got to something like almost 80%, which gets almost into convnet regime. Not quite, but there's some hope that fully connected computations can actually get somewhere. So this is just a side note. So now I'm going to kind of switch gears a little bit by talking about this orthogonalization point of view a little bit more from the perspective of recurrent nets. So all of you, or most of you, know LSTMs, which are now completely dominating anything that's being done in RNN research. And so in some sense, what's happening in an LSTM is that you have units that are connected to themselves by a constant 1 connection. And in some sense, this is, of course, an orthogonal transformation that's being utilized there, right? So the identity matrix being an instance of an orthogonal transformation. And even though the identity as a transformation is entirely useless by itself, The smart idea in LSTMs is that you put in all these gating mechanisms which protect this useless stuff and make it usable for the rest of the network. And suddenly something like remembering a value for a long time can get harnessed and can become useful. So the question is, can we extend this idea, the LSTM idea of retaining a value, to do something somewhat more dynamic in a sense, and still utilizing the fact that you get the fact that you get eigenvalues 1 by switching from identity to some orthogonal matrix. So here's an example of what one could try to do. You have the beginning of a sine wave, say, and if you are asked to continue the sine wave for infinity, that's very easy to do. It's nothing other than applying an orthogonal transformation matrix multiply to this piece of sine wave, and that's going to generate the rest. And it's going to do that forever because the eigenvalues of that matrix are 1 of that orthogonal matrix that does this continuation. And up to numerical problems, of course, in principle, you could do this forever without ever blowing up or vanishing or something. So in some sense, a sine wave is a really low information kind of signal, because you don't need to do anything other than it does the same thing over and over again, so it doesn't contain any information. You don't have to create new information as you keep generating that signal, right? And so what's interesting about the steerable view now is that since an orthogonal transformation gives rise to a representation that's steerable, if you phase shift this sine wave by a little bit, then that very same transformation is going to do the job still. So shifting a sine wave that starts like this, it's going to be the same as shifting a sine wave that starts anywhere else, because the transformation doesn't care about the initial phase of the signal. Unfortunately, this is only going to work for one sine wave. If you would just take a network and use orthogonal weights in there. So let's borrow from the LSTM trick and put in gating units to make this useless computation useful, the computation that just oscillates forever. So we can just add gating units, turning this whole thing into a mixture of experts, where from time step t minus 1 to time step t, you perform an orthogonal, hopefully, potentially transformation. But you have gates which allow you to blend in and out other kinds of transformation. So for one thing, you can at least now, in this simple toy example, deal with multiple frequencies, because you could just blend in the right matrix that does the transformation for the particular frequency at hand. So we played around with this idea a little bit. The question is, if you really want to take this literally, if I give you the beginning of a sequence, continue it, of course you would have to train the model to give it a seed and tell it what it is that it's supposed to generate. And then hopefully it will figure out from the seed what you want and then be able to generate the rest of it. So Vincent Michalski, who was a master student in Frankfurt at that time, played with that a little bit. And so the idea there is to take 2 frames from some sequence, infer those gatings, which I call M for mappings here. And then if we, for example, just simply assume that the mappings are going to be constant, so that the seed really tells you everything, the frequency and phase of the sine wave, then we could just assume constancy till the end of time and just keep generating the stuff that we want the model to generate. So here's an example on that sine wave. So you seed it with a little bit of red sine wave, and then you ask it to generate, and the red stuff here, I believe, is actually the model, and the blue stuff behind is the ground truth. And so it, after having been seeded with some sine wave, it continues. And so since this is an orthogonal transformation that it learned, of course, from the data. So actually, I should mention how this is trained, right? So you infer the mappings, you assume constancy, and then given a seed, you generate a very long sequence, and then we use backprop through time to just train this whole network. So since this is an orthogonal transformation, you can just keep generating, keep generating, keep generating. It's just never going to blow up because it just performs rotations, right? So there's no issue. And so you can go on forever. And so similar to LSTM, you can just retain a value for a long time. But in this case, it's a dynamic pattern that you cannot keep issuing through time. An interesting perspective onto this is by looking at what happens in an orthogonal transformation. Actually, an orthogonal transformation can always be decomposed into a matrix that is block diagonal. That's true of orthogonal matrices in general, where the diagonal blocks are just rotations, two-dimensional rotations. So every orthogonal matrix, including the one that shifts the sine wave along, is just a block of two-dimensional rotations. And so rather than applying an orthogonal transformations, you might as well just project into those subspaces and then just rotate, rotate, rotate in 2D and then project back, right? That's equivalent. So that suggests viewing what this M does as extracting a rotational derivative, because it just reads off phase angles, basically, from adjacent frames. And so once we're talking about derivatives, so the M's in that mixture model here, right, which are unfortunately called Z here. Since they're derivatives, they're just going to tell you by how much did you rotate around in one of those subspaces of those orthogonal transformations. But once you're talking about derivatives, that of course suggests maybe we can go one layer higher and talk about acceleration. So applying the very same model on the variable that represents that derivative. So we just stack another one of these a mixture of experts things on top, and now if we have 3 seed images that we show the model, it can infer 2 velocities from that, 2 mappings, and then from those 2 mappings it can infer 1 acceleration, which tells you how the velocity changes over time. And then assuming constancy of the acceleration, for example, in this case, so assume the acceleration now stays constant, which is slightly more interesting than having the velocity constant. You could say it's constant, and then given, so that's why I know the second acceleration. In fact, I know all of them. But given the second acceleration and this velocity, I can generate this velocity. And then from this velocity and this image, I could generate the next image and so on. Of course, you can go as high as you like. And it turns out there are actually words for this. So if you go beyond acceleration, the first derivative of acceleration is called jolt or jerk in the physics literature, apparently. And if you go higher, you get things like snap, crackle, and pop, which are really called like that. And what's interesting about this model is that it's orthogonal in time, because potentially, right? So it can learn things that don't forget, that keep doing the same thing over time, but it's contractive in layers in some sense. And so that's, for example, reflected in the fact that actually these mapping units that do the mixture idea are something like sigmoidal units that encode invariance because they are sigmoid. They can be constant for various inputs. Whereas the transformations that go from one frame to the next are just linear transformations. And so that by that they can be orthogonal transformations. This is also related to tensor nets by Richard Socher and others, because this is all based on 3D tensors, because a mixture of experts is going to have many linear transformations stacked side by side, giving rise to a tensor. Okay, so one way to make this the training work well, it turns out, is by asking the model to predict many time steps ahead and then backpropping through the model. This is very different from how most LSTM-like and simple RNN models are trained, which just try to predict the next, showing the model the ground truths up to t-1, right? You always do what might be called teacher forcing. You show everything up to t-1 and then ask the model to predict the next value. And then you show everything up to t and then ask the model to predict t+1 and so on. So that didn't seem to work very well with this model, where you actually should really generate for a long time before doing an update. So we came up with a way to make this work. Unfortunately, this is not going to work right out of the box, because if you generate for a very long time and you have initialized your model somehow, it's immediately going to go off to some weird place in space, and so it's going to follow some weird trajectories. It'll never do what you want at all. And so what we call anneal teacher forcing is a way to make this work by initially cheating, by giving it the ground truths, and then slowly corrupting that with more and more noise until eventually the model doesn't have anything but noise and has to turn that into a sensible sequence. So here are some simple experiments that demonstrate that acceleration works, for example. So chirps is a class of signals which are sine waves that change their frequency over time, and so you can accelerate, decelerate on test data, and it all works fine, and it works much better than vanilla RNNs, for example. Another thing that you can do is condition the frequency on an external input, so do actual control. Since we have a handle on frequency, we can just change the acceleration, we can just have a knob. David Kruger and Dustin Webb recently tried just generating sine waves where you tell it go faster or slower and so on. So basically doing time warping as a function of external control input. So have a slider that just changes the speed at which the model generates stuff. So far we haven't gone beyond those sine waves in doing that, but one could of course imagine doing something similar with music signals or whatever. Harmonics, which is the superposition of sine waves, works just out of the box as well, even though I suspect that LSTMs can do that as well. But simple RNNs were, I think, assumed not to be able to generate harmonics like this, which is incidentally test data in this case, which is several sine waves superimposed. We played around with videos. I think I'm running out of time, presumably. How much time do I have left? 2 minutes? Okay. So we played with videos where it turns out that this multi-step prediction makes a really big difference versus just one-step prediction. So even though a simple model trained similar to a vanilla RNN that just predicts ahead one generates stuff that is sensible, in order for it to generate stuff that really looks like the ground truth, which is shown on top, you really needed multi-step ahead prediction and stuff like that. So this is a somewhat subtle data set. It's an accelerated rotation, which is kind of hard to get your head around when you just look at it. You can classify those rotations, and it seems to work, and it works better than just looking at the mappings. And so we kind of basically show that, yes, the second layer does encode acceleration as it is supposed to. Here are some filters. I was very excited when I got this bouncing ball stuff to work a couple of months ago. Which is a data set that has been used by Ilya and Andrei Mny and others for some time, and it works and so on. But then it turns out LSTMs work just fine on this as well. As at the moment, I don't know if vanilla. If anyone has anyone tried vanilla RNNs on this? And vanilla meaning just ReLU, simple hidden to hidden, probably not. It didn't seem to be possible to do that, but well, maybe it's possible to revisit that and make it work. Just the final thing I want to mention, this is completely ongoing researchy stuff. It's very hot these days to talk about neural Turing machines and memory cells and memory networks and so on. So here's a way to turn this into a memory-like thing, to follow the trend. This is the last thing I want to say. If you just take this network and add some hiddens, just declare some of those units to be hidden. So that means when you train it, you compute cost on these guys, but you just let these guys do whatever they want. So the model can decide to use those units in any way it likes to. Then something interesting happens, actually, even though we haven't yet really explored this deeply. So you have a matrix that maps this vector to this. So as part of that, you're going to have some submatrix that maps the visibles to the visibles, and some submatrix that maps the hiddens to the hiddens, and then a part of that matrix mapping from the visibles to the hiddens and from the hiddens to the visibles. And what's interesting is that this network in this whole hierarchy can decide when to switch on and off what kind of transformations. So potentially it could say something like, okay, I think it's time now to move some information from those visibles into the hidden space and then keep doing something in that hidden space. And then at some point it can decide to just read that out and use whatever has happened in that hidden computation. So the last thing I'm going to show is a little video of a single bouncing ball that disappears behind an occlusion. And so this is one of various examples, of course, but it seems to work that the model is able to generate that bouncing ball video, even though for a couple of frames it's not able to see anything but black. So the hope is, of course, that by means of its hidden units, it's able to shovel some of the ink of the ball into some hidden space, in which case it can permute things and it can learn for how long it has to permute things and so on. So it can sort of in its mind keep continuing that transformation so that at the right time the right moment in time it can read that out and write that back into the image buffer. If that's really what's happening here, that's unknown at this point, but this is just one of the ongoing things that we're working on. Okay, I'm just going to stop here and let you ask questions. Thank you.